Okay, second to last unit of the year. So feeling pretty good about the year so far. This one's all about mathematical reasoning. So we're going to go through and we're going to look at inductive reasoning to begin with, and then deductive reasoning, and we're going to be talking about proofs and arguments and puzzles at the end. There's actually a whole unit on puzzles, and there's definitely going to be a puzzle or two on the test. So maybe we'll take a fair bit of time to practice the puzzles. Okay, inductive reasoning. So can you make predictions, and can you talk about your predictions and test your predictions? Number one, complete this investigation with a partner. So pause this. Don't take forever though. Like 5, 7 minutes at most. Try and finish this with a partner really quickly, and then unpause this video. Okay, if you've unpaused it, I'm about to start again. So Frank thinks that figure 10 in this pattern will have 100 triangles, and all these triangles will be congruent to triangle in figure 1. They are going to be all congruent. We can kind of tell by the shapes that they're all the exact same shape, they're just bigger. So how did he arrive at his conjecture? What does a conjecture mean? That's a guess. Organize it into the following tables. So figure 1 had 1 triangle, figure 2 was 4, figure 3 is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep. And then he continued this pattern. What do you notice about the data in the table? It's the figure number squared equals number of triangles. That seems to be the pattern that holds. Whatever your figure number is, just square it. So 5 squared is 25. Extend the pattern 2 more figures. Well, 9 would be 81, and 10 would be 100. What numeric pattern do you see in the table? Maybe that's what they meant. So it's the number of triangles is the figure number squared. Is Frank's conjecture reasonable? So he said in figure 10 there would be 100. Does this seem reasonable? We can't really know for sure without drawing it, but does it seem like a reasonable guess? Based on these figures, it certainly does. We might want to try figure 4 maybe. So we'd have a line there, we'd have a line there, and we'd have a new line there. And this one would contain 3 triangles, and this one would contain 5 triangles. And this one now would contain 7 triangles. 1, 2, 3, 4, 5, 6, 7. So 7 plus 5 plus 3 plus 1 is 4, and 9 is 16. So it is indeed 16. Yes, fits the pattern. Till figure 4. So it's a reasonable guess at least. Maybe we don't know completely without actually drawing the picture. Did I actually get that in my thing? But I think it seems to be a reasonable guess. Oh, a couple more questions. How did Frank use inductive reasoning to develop his conjecture? He took, I'll just say it out loud. He took what he saw in the first 3 figures, he wrote them down into a table, and then he noticed a numerical pattern from the existing numbers, and he extended it to the future numbers. That's really what we mean by inductive reasoning. Basically, I think of it like extend a pattern. So what do you notice, and can you make it into a bigger rule, basically? Is there a different conjecture you can make based upon the pattern you see? Explain. Any other way to explain this table? At least for the first 4 terms? Well, you're adding 3, you're adding 5, you're adding 7. Oh, actually I like that. Plus 3, plus 5, plus 7. So we could assume there would be a plus 9, a plus 11, a plus 13, and a plus 15. Let's test this one. Is this actually plus 15? So 64 minus 49 is indeed 15. So we could actually notice it that way as well. So there's a couple different patterns. And both would work just fine. They're actually the same pattern, different ways of talking about it. So adding, increasing odd numbers. Is another pattern. Okay, here's our definitions. A conjecture. A conjecture is a testable expression that is based on available evidence but is not yet proved. Okay? So this is all about conjectures in this one. We're going to get to deductive reasoning eventually, and deductive is going to be proving it right from the start. Conjectures are using inconclusive evidence to make a guess, basically. This is like our hypothesis in science. Inductive reasoning. So I called it up here, extending a pattern. Inductive reasoning, a more perfect definition is draw a general conclusion by observing a pattern and identifying properties in the specific examples. So this is a big part of logic in philosophy, and I used to do a lot of logic, so I'm pretty comfortable with this. Basically what this says is if you've seen 10 white rabbits in a row, you've never seen anything but white rabbits, you're just in a new territory, so you would guess that every rabbit in that territory is now white. So it's not proven, it's just a guess based on observed data. So it's always getting bigger is the big thing, and that kind of comes from here. A general conclusion is a bigger rule. So some people like to talk about this from going small to big. So I've seen 10 rabbits, that's the small, so I conclude all rabbits are white. That's the big. What conjecture could you make about the following situations? Eli has lunch at the same deli every day for a week. Each day, the special of the day has included fries. Based on this, what can Eli conclude about the next visit to the deli? The special will The special will include fries. Now, he doesn't know that for sure, but it seems to be a good guess based on the available evidence, because it has been every single day so far. They've always thrown the side in with it. Justin arrives at his first book class at 8:10 a.m. Every day for the past 3 days, his teacher has arrived between 8:12 and 8:14, and the class starts at 8:15. Therefore, we can conclude that tomorrow, his Block 1 teacher, ... will arrive. Maybe we'll mix up the way we say this. Will arrive 1 to 3 minutes early. So we're guessing that he's going to be there just before the class starts. Not a great prof. Usually you want to be there a little bit earlier than that. With a partner, use inductive reasoning to make a conjecture about the following situations. Okay, so try it on your own now. There's going to be 1, 2, 3, 4, 5, 1, 2, 3, 4. 4 theories. Pause the video for maybe 10 minutes and try and do these really quickly on your own. I'll unpause it in about 5 seconds. Okay. If you add 2 odd numbers, so they're not all as easy as this stuff up here. If you add 2 odd numbers together, like 1 and 3, I get 4. What about 5 and 7? I get 12. What about 3 and 9? I get 12. What conclusion can you make about these? Any 2 odd numbers, so you would have to have a decent sample size. You might want to try at least 3. Maybe 4, 5, 6, 7, depending on how quick you can tell this. I would conclude 2 odds, add 2, and even. That's a good conjecture, I would say, based on inductive reasoning. So it's actually both of our words. That is a conjecture based on inductive reasoning. And it also happens to be true. Every two odd numbers added together will be an even number. Okay, multiply an even number by an odd number. 1 times 3. Even number times an odd number, sorry. 2 times 3 is 6. 4 times 5 is 20. 6 times 9 is 54. Repeat it several times. What conclusion can you make? Even times odd equals even. And that is true. That's our conjecture. It's based on inductive reasoning, and it's also true. An even times anything will make an even number. Construct several scalene triangles. Do we remember what scalene means? All three sides, different lengths. Measure each of the angles and each of the sides. Note the relationship between the smallest angle and the measure of the smallest sides. Let's do this twice. So, I'm going to kind of number these 1, 2, 3 for small, medium, large. This one looks to be the biggest, second biggest, smallest. Where's my biggest angle? That's my biggest angle. That's my second biggest. That's my smallest. Let's try another one. And when you're doing these, it's really important. I didn't actually highlight that before, but you want to pick things that are a little bit different. You don't want to do 2 times 3, then 2 times 5, then 2 times 7, because then maybe it's only true for 2. So you really want to mix up your examples to test out your hypothesis. So what's another triangle that's very different than this one with 3 different sides? Maybe an obtuse triangle. Okay, that's an obtuse triangle. It's quite a bit different than my last one. That's my biggest side, second, third, biggest angle. Which is my second biggest angle? It's going to be that one, and that's going to be that one. Okay, can we see the relationship here? The largest side is opposite the largest angle. Is what I would hope you to notice in this one. And I'm going to be fairly picky. You should be able to actually tell this. If you can't tell a good conclusion yet, you haven't done enough examples. So create a couple more, try them. And we can be a bit more robust than this. We can say that the size of the angle is always opposite its counterpart. The size of the side is opposite its counterpart sized angle. So largest side is opposite largest angle. Smallest side is opposite smallest angle. And the like. They're always partnered with the opposite angle. And we talked about that during our trig unit, so hopefully that kind of makes sense. Construct several pairs of intersecting lines. Measure the pairs vertically. Measure the pairs of vertically opposite angles. Pairs of intersecting lines. Measure this angle and this angle. And what do you notice? Now a line has to be straight, so you might need to use your ruler. What's another pair? Very different. The vertical opposite angles. What do we notice about them? Maybe try another one. What could look very different than that? That one's very different. Which two would we say is vertically opposite? Maybe that and that. They should be, and we already know this from another unit, vertically opposite angles are equal. Okay, that's it for this one. Does a conjecture, big rules though, does a conjecture prove the theory? No, it's just a guess. And it doesn't even prove it if you do more examples. So I can make another 20 of these lines, and they could all still be true that the vertically opposite ones are equal, but I still haven't proven it. Proof is very, very extreme. A proof means I've shown it must be true for every possible pair of lines. So maybe there's a pair of lines that I can draw that I just haven't thought of, where it's not the case for. So a conjecture does not prove it. They're only more or less accurate guesses. Can you prove it for every case? Not through examples. There is other ways to kind of prove these things in a more robust way, and we'll look at those in the future. Okay, 16-minute lesson and probably an extra 10 minutes in do-it-yourself stuff at least, but still not too bad.